In this talk, we present balancing discriminability and transferability for source-free domain adaptation. We deal with domain adaptation where knowledge has to be transferred from a labeled source domain to an unlabeled target domain. We begin with preliminaries. Discriminability is the ease of separating different task categories with a supervised classifier, and transferability is domain invariance of features. For example, assume that color represents domain and shape represents class. High domain separability yields low transferability as features lack domain invariance, while high class confusion yields low discriminability as classes cannot be separated by a supervised classifier. Based on this, we get the other combinations. The final case where both are high is desirable for DA. Now we discuss the trade-off. Removing domain specificity for better transferability usually lose entangled task-specific information which hurts discriminability. Thus, improving one hurts the other. For example, in segmentation DA, contours improve transferability but reduce discriminability as task-relevant color texture are lost, which hurts adaptation. Now we ask, can we strike a balance between them? Prior works propose modified adversarial DA towards this, but require concurrent access to both source and target data. These are unsuitable for a source-free setting where data sharing is restricted. We operate in a vendor-client paradigm where vendor trains a model with labeled source data and shares only the source model with the client for adaptation. Now we discuss our key insights. First, we analyze prior DG and source-free DA works. Most SFDA works focus on preserving discriminability without labeled source data, whereas most DG works focus on maximizing transferability without target data. A natural question arises, why is striking a balance crucial in source-free DA? Under source-free paradigm, discriminability can only be gathered on the source side with labeled data. Thus, the trade-off becomes more severe as discriminability cannot be preserved using only unlabeled data. An explicit effort to improve the trade-off operating in the green region can benefit SFDA. Now, what are the key design aspects to improve the trade-off in SFDA? A naive solution is to translate source and target to a generic domain with high transferability and discriminability. But such translation leads to loss of discriminability. Thus, to strike a balance, we propose mix-up between original and corresponding generic domain translated samples. Next, we describe our approach. The obvious question is how to obtain generic domain samples. A realizable generic domain must possess high transferability. Based on this, we propose two generic domain translation methods. First, an input edge representation can be obtained through contour estimation. Intuitively, edges preserve the shape and remove the domain dependence of color and texture. Second, we propose a feature-space generic domain representation. A set of task-preserving image augmentations simulate novel augmented subdomains. The augmented feature mean diffuses the domain variance and is used as the generic domain feature. Next, how to perform mix-up. As per our insights, we mix up the original and corresponding generic domain samples. A simple convex combination with a fixed mix-up ratio works well and validates our insights. Now we discuss the training algorithm. Our approach can be combined with any existing SFDA work. Assume a vendor-side algorithm VS-algo that uses the original source data DS and a client-side algorithm CS-algo that uses the original target data DT. For training, we simply use our proposed mix-up datasets DSM and DTM as shown. Next, we illustrate our key quantitative results. First, we evaluate single source DA on Office 31 and VISTA benchmark and observe consistent gains. For the classification task, we observe that feature mix-up consistently outperforms edge mix-up and produce state-of-the-art results. We also evaluate segmentation DA and observe significant gains over all settings. Here, edge mix-up outperforms feature mix-up as it better suits dense prediction. Here we present qualitative results for single source and multi-source DA. Our adapted model generalizes better than the prior SOTA. In summary, we analyze existing DG and source-free DA works and find that SFDA works prioritize discriminability while DG works prioritize transferability. Conversely, we seek a suitable balance between the two and propose mix-up between discriminable original samples and corresponding transferable generic domain samples. Finally, we demonstrate gains over the SOTA with faster convergence across multiple source-free DA settings. Please refer to our paper and project page for more details. Thank you.